Awesome. Let's see here. Let's hit share. Hey, everybody. My name is Alex Merced. I'm a developer advocate with Dremio. And today we'll be talking about a really interesting topic, Apache Iceberg. We'll be taking an architectural look under the covers. Now, I do encourage you to follow me on Twitter. If you're on Twitter, you can follow me at AM Data Lakehouse. Also, feel free to add me on LinkedIn. I'm always posting a lot of new content specifically about the Data Lakehouse, uh, technologies like Apache Iceberg, Apache Arrow, Project Nessie. Some of these things will come up as we go through. But in today's presentation, we're going to be focusing on this agenda. So first, we're going to talk about what's a table format, because Apache Iceberg is a table format. And it's like, well, what is that? So let's talk about that. Why do we need a new one? Like, I thought I heard that there was like this Hive thing that everyone was already using. So why would I need something else? And the architecture of Iceberg. So like, what is the secret sauce? Like, what is it about Iceberg's design that makes it so special and makes it so unique in this particular space? And then we're going to show some examples of some transactions to kind of see like when I run a transaction on a Iceberg table, what's actually happening under the hood, to kind of just see that special sauce in action. And then we're going to summarize sort of like all the benefits. So we'll show you a cool test case from like Netflix, so you can see like what the performance benefits and the effect it had on their systems, and just kind of go over many of the really cool features that this brings to the data lake. So that'll be today's adventure. Now, let's start off with that question. What is a table format? So let's just set the stage for like the problem. So what happens? Once upon a time, you had data stored on Hadoop clusters, and what we would do to run analytics on them is we'd use this system, a MapReduce, where you'd write these JavaScripts, and you would have to sit there and say, okay, well, these files stored on the data, that's my data set. I want to do these operations on them. Not, it worked. It was great. Um, but it wasn't the easiest thing to do. So then eventually Facebook creates a thing called Hive. And the idea behind Hive is to say, hey, let me write an SQL statement, and that SQL statement will get translated into a MapReduce job. So that way, instead of writing a JavaScript, I can just write an SQL statement, which, more people know SQL. SQL is going to be, that sort of declarative style is going to be a lot simpler, just makes life a lot easier. But the thing is that SQL kind of depends on this whole idea that there's a table, okay? And we take that for granted when we're using like a database or a data warehouse. There's just tables. We put the data in the database or the data warehouse. It's a table. We don't know how that table's organized under the hood, how the data is stored, how it runs those queries. Nor generally do we care. We have this sort of in the box experience, okay? Problem is, what happens when you want to use other tools? So basically what happens is that Hive comes up with a way of saying, how do we know which files in your data storage, in your Hadoop cluster nowadays, in your cloud storage, like an Amazon S3 or Azure or Google Cloud? I may have these 1,000 Parquet files. These 1,000 Parquet files are really just one data set. How can I make sure that my systems, the query engines, the tools that I use, recognize those 1,000 Parquet files as one singular table? And that's the job of a table format. It does what you just take for granted in a database and a data warehouse. It defines that idea of a table. It'll say, hey, these 1,000 files over here are just one data set, and I can now write them in SQL and treat them as a singular data set. I could write Python scripts in a Python notebook and treat them as a single data set, instead of me having to sit there and constantly define these 1,000 files are the data set. Which, again, if you do that manually, that could result in inconsistency because people might not select the right 1,000 files and things like that. So this gives us a nice consistent way of saying, this is the table, this is the thing I'm analyzing. And the way Hive did it, what they did is they took a directory-based approach, which worked very well. It basically said, this folder is a table. Any files in the folder is part of the table. So that way when a query engine, because this is again specifically designed mainly for a data lake, okay, not necessarily applicable to a database or a data warehouse, because again, those are going to have all these kind of details abstracted built into the box. But now we have sort of like this world where we have our data storage, and our data storage is going to be different than the tool we use to analyze the data. And now we're going to have this layer that allows us to create this table abstraction when we're working with the data lake. So Hive said, hey, if you have a folder, I'm going to treat that folder as the table. Any subfolders will be treated as a partition, and we'll just kind of work with that assumption. And that worked very well. Okay. But it did kind of have its downsides. But at the time, hey, just being able to like know it's a table, be able to run my SQL and take that SQL, turn it into a MapReduce job and run that on that Hadoop cluster, that it was great. Made life a lot easier for a lot of people. And because of that, it became sort of the de facto standard. I mean, people still are using Hive on a daily basis. Um, and being that de facto standard, pretty much every tool works with Hive, okay, which is one of the benefits of Hive. It allowed us to do sort of use very efficient query patterns that we were maybe used to using with like databases and data warehouses, but bring them to the data lake, things like partitioning. People actually say, okay, my table, well, I'm breaking it up by, let's say, each year's worth of data, and being able to like query by year, I can now, instead of scanning all the data files, I'll scan just the files that are applicable to that query. So that's pretty nice. It was file format agnostic. Not everything had to be a Parquet file. It could be ORC, it could be Avro, it could be other things. Allowed you to use what you needed to use. It allowed atomic updates of a partition. So I could atomically update a partition because essentially we just kind of rewrite the partition. And then it provided us, again, that single central answer to what is a table. So I could have 5 analysts doing operations on the same table, and they're operating on the same data. Okay, sounds like something nowadays we take for granted, but once upon a time, you're writing those MapReduce scripts, you might have 5 different analysts, and they might have a different set of 1,000 files, so a slightly different set, giving you slightly different results of your data. Okay, but again, not perfect. That's why we needed a new solution. Small updates are very inefficient. So basically, if you really wanted to update like one record, you're pretty much updating a whole partition. It's going to take a long time. And not only does it take longer, but that also means more computing power, which translates into a bigger cloud bill. So again, anything I can do to reduce the amount of work that the query has to do, to reduce the amount of compute, is not only going to make my queries faster, but it's also going to reduce my cloud bill, which is always, these days, anything you can do to reduce that cloud bill is pretty nice. So there wasn't really a good way to like change data in multiple partitions safely. Again, having multiple jobs going on at the same time safely. You didn't have all these asset guarantees that, again, we take for granted when we're working with like databases and data warehouses that kind of put you in this nice sort of box, and as long as you're in the box, everything works just fine. And then basically, because we had this directory approach, what would happen is that there was all these file listing operations. I have to go in there, like list all the files in the directory, and then go through the folders and list all the files in those folders. And then I have to scan those files so that I have to open the file. And even if I'm using Parquet, which, we have these with Parquet files, you have these row groups and you can kind of do some fine pruning within the file. You still have to open the file, read the file, close the file, then open the next file, read the file, close the file. That really made these queries take longer than we'd like. So the idea is, how can we reduce these file operations? And when it came to the partitioning, that wasn't always like the easiest thing to use. So to give you an example, let's say I have a timestamp field in my data, and I would like to partition the data by year. What I'd have to do is that I have to actually create another field that represents just that year, and then partition based on that field. The problem is my data consumers, they're naturally going to want to filter based on the timestamp. So I would actually have to make sure that they were trained to understand that, hey, if you want to take advantage of the partitioning, you also have to make sure you do a filter on this other field, which isn't the most intuitive thing in the world. So if people forgot to, they're going to end up doing a full table scan. So the idea is like, okay, that's not ideal ease of use. So can we improve that? And the statistics were often stale because the stats were only updated every once in a while when you ran like an analyze query on the table, which would have to then scan the whole table and recompile all the stats. So we want to fix all these problems. Okay, and these were situations, these were problems that Netflix was running into. So Netflix had several goals and wanted to like find a new paradigm to kind of overcome these problems. Okay, they wanted more correctness and consistency. Okay, so basically I want all that correctness and consistency, but I also want faster planning, query, and execution. Again, one, because we don't want to wait for our queries, but two, of course, again, if we can speed up our queries in a way that reduces compute, that also means a lower cloud bill. So that's always very nice too. Okay, we don't want users to have to worry about like, oh, okay, there's these 3 other fields that have to do with the partitioning, and you need to make sure you filter by those fields. Is there a way we can just make it where they can just intuitively say, hey, let me just query the timestamp field. I want all data between this date and that date, and they would just automatically take advantage of any partitioning by month or by year or by day. Can we just make that easier? Table evolution. You know what? Sometimes I want to change how the table is partitioned. Sometimes I want to change what the schema is. I want to be able to actually be able to do that without having to rewrite the entire table. Okay, because that would often be the case with Hive. You want to change, actually pretty much in all other cases on the data lake, if you want to change the partitioning, you have to rewrite the table. If you want to change the schema, you may or may not be able to in Hive, and then with all the table formats, you can update the schema. But again, the idea is I don't want to have to rewrite the table every time the table needs to change. And to be able to do these all at scale, okay? Because Netflix is working here like petabyte, multi-petabyte scale. So not only do we need to have all these benefits, but we need to be able to do them at scale. So they come up with a whole different approach. So they say instead of defining the table as a directory, let's just define the table as a list of files. So it doesn't matter what directory or where on this file storage system the files are at, because we're going to list all the individual files. So even if they're in different folders in different places, long as they're on the list of files, they're part of the table. Okay, and this is going to unlock all sorts of really cool benefits. And this whole new paradigm becomes Apache Iceberg. Okay, first it's a project at Netflix. Eventually Netflix donates it to Apache. But Iceberg, again, as a table format, it's going to allow us to define what is a table on our data lake storage. So again, that could be a Hadoop cluster, that could be object storage, but specifically what it provides you, what the Apache Iceberg project provides, is a specification. Okay, so the idea is to create a sort of like uniform playbook that all query engines that write data can write the data the same way. So instead of every engine having to come up with like their own style of metadata to make queries more performant, how about we all have the same playbook for how we're going to write metadata? And that's essentially what Iceberg is providing. It's saying, hey, when you define a table, we're all going to write the metadata in this structure. So that way that same table can be used from this tool with this tool and that tool and this tool. Okay, when we define a table. To make that easier, they're going to create several libraries and APIs. So that way, when an engine wants to adopt Iceberg, they don't have to, create a whole implementation from scratch. There's plenty of Java and Python libraries that to assist in working with those Apache Iceberg tables. But what Apache Iceberg is not, it is not a storage engine. You don't store it's not like a storage, it's not a file format like Parquet. It's not a place to store stuff like a Hadoop cluster or cloud storage. It's not an execution engine. Apache Iceberg doesn't actually run queries. You would run queries with something like Spark, Flink, Trino, Dremio. Okay, you would run queries with a query engine. But query engines can then have the understanding of how to read an Iceberg table. Okay, and that's again the beauty of this whole sort of deconstructed database, because that's essentially what this whole idea, the data lakehouse, is essentially creating a deconstructed database, data warehouse, where basically the different layers are all separate. Your file storage could be, again, Cloud or Hadoop. Your files could be saved in something like Parquet or ORC. What defines them as a table? That'll be like something like Apache Iceberg. And then you can use the query engines, different query engines. You can use Flink for this, Spark for that, whatever you want. Okay, and the nice thing about that is that now you have your data in one place, defined one time, instead of having to ETL that data into each tool you want to use. Okay, and having all these different copies, because every database, every data warehouse needs you to restore that data, ingest that data again into their platform. Now you can just kind of work with all the data in one place. And then again, this is going to enable a lot of what you couldn't do with Hive yet, things like asset transactions and other things. So, and it's not a service. So Iceberg isn't some like process that you're continuously running. Okay, all the processes are going to be really like tied to the engines and other tools that you use. Really, Iceberg is just, again, that specification. How do we write our metadata? So that way, if we all agree on how to write the metadata, we can all agree on how to read the metadata and take advantage of it. And then this could work anywhere. Okay, so just to kind of see that structure, again, that specification, it's basically, this is it, this image here. Okay, so let's just demystify this image. So we start from the top, and we're going to work our way down. Okay, the first component is the Iceberg catalog. The way I like to think about the Iceberg catalog is like a phone book. Okay, so I mean, there's phone books still around, but I mean, I remember back in like the 90s, if I wanted to know where like, get Bob's phone number, I would go grab this big thick yellow book with yellow pages and flip through it, and I would look up Bob, and there was Bob's phone number, and I was able to get in touch with Bob. Same thing with a query engine. Your query engine is going to be thinking, where's table one? Okay, and it needs to know where table one is. So what it does is going to communicate with the catalog, and the catalog really is just going to be one of several different things. But all it really contains is one thing, a pointer to where the newest metadata file for that table is. That's essentially, that's its one job, to tell me where the new metadata file is. Okay. And that catalog could be, you could be using an HDF. There's a bunch of different catalog implementations. So you could use HDFS, which is like the simplest implementation. But if you have an existing Hive metastore, you could use that. There's a really cool tool I'll talk more about later on called Project Nessie that actually not only allows you to use Iceberg tables, but adds like Git-like functionality. So you could create like branches of your catalog and then merge those branches after you've done some work on them, and basically in the same way you would write work with code. And then you could also use like pretty much any relational database with the JDBC catalog. There's a DynamoDB catalog. It doesn't matter which of these you use, they all fulfill the same role of being the first place that an engine looks at. The engine's going to go to the catalog and say, hey, where do I find this table? And that catalog is going to then point them to the metadata file. And the way to think of the metadata file, it's sort of like the definition of the table. So this is the table-wide metadata. So it's going to have information like, where is sort of the default directory of this table? What is the schema of this table? What are the historical schemas of the table? Because again, the schema can evolve. What is the current partitioning of this table? What are the previous partitionings of this table? Because again, it can evolve. What is the current snapshot? So like, what is the current state of the table? What are the previous states of the table? Because we even track the previous states, which is going to enable some pretty cool features. So basically from that metadata file, the engine can identify, hey, which snapshot I want to query, and then just kind of know the layout of the table, the schema, the partitioning, all that stuff. But once it knows what snapshot it wants to query, it can take a look at that metadata, and that snapshot will point to another file called a manifest list. Okay, and a manifest list is essentially what defines a snapshot. So that's so basically we had the metadata file, that's the table-wide metadata. Now we have the manifest list, which is the snapshot level metadata. Okay, and so when we look at the manifest list, this is going to give me information. It doesn't tell me the specific files that are part of the table. Okay, what it does is going to list a bunch of groups of files. Okay, and each group of files is referred to as a manifest. So that's why it's called a manifest list, because it lists manifests. And the cool thing about this is that at this point, the engine can begin planning the query smart. Because what I can do is I can take a look at the metadata in the manifest list for each manifest and take a look at the partitioning that that manifest represents. And so essentially, if the user queries on some field that the table is partitioned by, I can begin saying, okay, hey, this group of files, I don't need this group of files because it's not, based on the partition field, it's not something I need for this query. And then I can just keep kind of getting rid of big chunks of files. Okay, don't need to scan this, don't need to scan this, don't need to scan this, don't need to scan this. Now, once I've done that, basically I've removed everything that doesn't apply to my partitioning for this particular query. Okay, so I queried for, like, let's say a particular year. I can filter out all the manifests that cover data outside of that year. I would then go scan the remaining manifests. Okay, so at the end, I'll have a few manifests that remain, and those manifests will actually list individual data files. But they don't just list the file. They have additional metadata on the file, such as column metrics. So I can figure out what is the upper and lower bounds of each column for the records in that file. The benefit of that is like, hey, I queried within this year, but I also queried for, I said, hey, I want to get everybody between the height of 5 feet and 6 feet. Okay, it can actually use the column metrics to sit there and say, okay, this file doesn't have anybody within the range we're looking for. This file doesn't have anybody within the range we're looking for. So that way we can reduce even further the amount of things we have to scan. Because the less things we have to scan, the faster the query, the cheaper the cloud bill. Okay, we win-win. So basically we get the smarter query planning because of this metadata. Okay, so basically at the manifest list level, we can filter based on partitioning. Once we get down to the manifest files, we can then filter individual files based on their column values and get the narrowest number of files we need to scan. And then after that, we take that list of files and then scan those data files. And this enables any query engine to be able to take advantage of this pattern. Okay, so basically, whatever tool you're using, Iceberg is going to give you sort of an initial boost out of the gate. Okay, Cool. So before I go on to the next section, I'm going to just take a few of the questions that I see coming on in. Okay. Do I have a handy list of engines that support Iceberg? I do. If you go to dremio.com/subsurface, that's where we post a lot of articles about Apache Iceberg, Apache Arrow. We have an article that covers comparison between the three main data lake table formats. That's Apache Iceberg, Delta Lake, and Hoodie. And in there actually is a list of not only what engines support Iceberg, but whether they support reading and or writing to Iceberg. So that whole list will be there. Cool. Are manifests used in Lou's statistics? Well, a lot of the statistics are in the manifest. So essentially the manifests are the holder of the stats. So basically, instead of having to run an analyze query, oftentimes if you need table stats, you can just basically go to your manifest and your manifest list and basically extrapolate the data from the manifest. Can the location in this be anything else than S3? Yes. Again, it could be a Hadoop cluster. There's an HDFS implementation, and it works with any object storage. Like the object storage implementation, it will work with pretty much anywhere you want to store your data. I'll oftentimes just say S3 just as an easy example, but it works with Azure. It works with Google Cloud. It works with any kind of cloud object storage and any situation where you have a on-prem Hadoop cluster or an EMR Hadoop cluster. It works. Because essentially all you're really doing is you're writing some JSON data in the JSON file and some Avro files. So it works. Cool. And then on to this is the last question. Looks like tables can have multiple formats. Is that okay in practice? They can have multiple formats. There's pros and cons. I mean, I can imagine some situations where you might have ingested data as an Avro format, so you might temporarily have it as Avro, and then you turn it back into Parquet after compaction. But I mean, probably generally, I'd imagine like you'd want to keep things as consistent as possible. Cool. But with that, on our next section, what we're going to do is we're going to take a look at some transactions. So we're actually going to do queries, see how that query would play out, just purely based on Iceberg alone. Okay, so in this case, again, any engine you use might have other optimizations and other considerations. So always keep in mind, like Iceberg is a specification, but each engine has to implement that specification. So there will be like differences in like what catalogs different engines support and what sort of features of Iceberg they support. But Iceberg gives the tools that any engine could support all these features if they choose to implement it. So again, always take a look at what is the level of support the tools you're using. But basically, if I run this create table statement, what's going to happen is, again, it's just like a standard create table statement. I'm specifying the schema. This using Iceberg clause is specific to Spark. So this is kind of assuming Spark. Just tell Spark that, hey, we're making an Iceberg table. Now this partition by clause. Now let's examine this for a quick second, because this is actually pretty cool. Okay. So notice how instead of me just saying, hey, I want to partition based on the order timestamp field, I kind of pass it to this function hour. There's several transforms in the Iceberg spec. So basically what it does, when I do that, I'm not saying I don't have to create a separate hour or year or day field. Basically what's going to happen is that now that's going to be in the metadata, and basically it's going to know to track the data based on this field, but based on hour. And you can also do day, there's year, and then there's other like non-date ones like truncate. So you can actually like partition based on a truncated value. So that could be useful for something like names. So like, hey, I just want to partition based on the first letter in people's names. I can use the truncate partitioning. There's a bucket partitioning. So that way, you know, maybe there's like a lot of different possible values, but I really just want to break them up into like 16 buckets. So you have a lot of options with these partition transforms to be able to optimize your tables in ways that might usually not be available to you. And again, good partitioning means good performance. Okay, so right there I'm saying, okay, partition this table by the hour. So track the hour that that field is in, and break up and segment the data based on that. But essentially, there's only one thing we need here. We're not going to write any data files because there's no data in the table. And if there's no data in the table, there's no files to list. So there's no manifest listing files. And if there's no manifest files, then there's no need for a manifest list because there's no manifest files to list. So in that case, the only thing we really need is a metadata file. Okay, so we write the metadata file that defines the table, and then we head over to our catalog and tell the catalog, okay, we just created this table called table one. So if anyone asks for table one, point them to this metadata file. Okay, and that's it. And then what you'll see, like written in your data storage, again, whether that's cloud object storage or a Hadoop, you're going to see basically files created somewhat in this structure. Okay, so it's basically you still have a directory and you have a metadata directory and a data directory. This is the default way of doing it. But because Iceberg isn't tied to the directory approach, it doesn't have to be this way, which I'll bring up again in a little bit. But see, right now, all we have is this metadata.json file. Now let's run another transaction and actually put data in this table. So I'm going to insert some values. Yay. Now, basically what's going to happen first is it's going to determine what needs to be written as far as data files go and write those data files. So it's going to write any data files that are required to write for this particular query. Then it will write the manifest file because I can't write the manifest file if I know what the data files are. Then that manifest file can then be written into a manifest list. We define the snapshot. But everything's immutable in data and like this whole like data lake table format world. So all data lake table formats, everything's immutable. Nothing is ever altered. So instead of altering the old metadata file, we write a new metadata file. But the new metadata file has the information on the old prior snapshot and the new snapshot we just created. And then we go back and we update the catalog and we tell the catalog is like, okay, don't point to that metadata file anymore, point to this one. So now next time a query comes in, the next query that comes in will be routed to that new metadata file. And then that's how you get this like consistency. So I could be doing an update in Spark, but a query coming in from Flink will also be able to accurately get the right information because it doesn't matter who's hitting the catalog, they're always going to be directed to the same metadata. So basically updates across tools are instant. Now, let's do an upsert. Okay, so basically I have my table one, and I have a staging table, which I want to merge against my table. So I do a merge into, so table one, and then that's going to be known, and then we're going to query our table one staging, which is going to be known alias as S. Okay, and then basically anywhere where the order ID on table one matches the order ID on our staging table, we want to check, we want to merge. So if they match, then we're going to want to update the record. And if they don't match, then we're going to want to insert the record. So that's what this query is doing. So once again, the query engine is going to go do the job and start processing, hey, what new data do I really need to write here? Because again, if there's existing data that doesn't change and we can use the old data files, we're going to use the old data files. Okay, and that's another nice thing about this design. You can reuse data files much more easily. And you can actually even reuse manifest files. So a manifest file can be used for multiple snapshots if nothing's changed. Okay, and that just really allows for maximum reuse for maximum performance. So we write any new data files that need to be written, and then we write a new manifest file that'll list any of the new data files and any of the previously existing data files that would be part of this query. And then once again, we write a new manifest list defining a new snapshot. We create a new metadata file with all the new snapshot and all the previous ones. And then we update the catalog and say, catalog going forward, point to this metadata file. Okay, as you can see here, like the files, all the files still exist. Okay, so I have all my snapshots and like the metadata you see is just JSON and Avro files. Like all that metadata is just inside JSON and Avro files. But I still have so like this grayed out Parquet file is not part of this snapshot, but it still exists because I'm going to be able to time travel and query those previous states of the table. So we have all those files there, and that's the beauty of the immutability. I know that the old stuff's going to be there, so I can query those old versions of the table. Cool. And let's run another query. So here we're just going to do a standard read query. So now we're done writing to the table. So since we're not writing to the table, we don't need to create a new snapshot. Instead, we're going to go through that query pattern we kind of mentioned before. The query engine that's reading is going to go to the catalog and say, hey, I want to query table one, figure out where the metadata for table one is. Well, I didn't specify a particular snapshot, so it's just going to assume the newest snapshot, the current state of the table. It's going to go look at the manifest list for that snapshot. Okay, begin doing its filtering, except for this case, we're selecting all, so it's just going to grab everything, and then grab all the files and then scan the files. Okay, so pretty straightforward. Okay, and then now we're going to do another query where we actually filter. Okay, and we'll take advantage of the partitioning because we're filtering based on that timestamp field. Okay, and even though I didn't specify like a specific hour, so this is where like Iceberg gets real nice. Even though I didn't specify a specific hour, it's still going to take advantage of the partitioning because I'm still filtering based on that field. So it'll still go in there and try to figure out, okay, hey, which partitions apply to this date, which is nice. So again, the user doesn't have to really think about how they do their query. If they just query the right fields, they're gonna take advantage of the partitioning. So what's gonna happen here is that once we go through the same pattern once again, I'm gonna go to the Iceberg catalog, say, hey, where's table one? It's gonna direct me to the metadata file. I'm gonna go figure out what's the newest snapshot, go to the manifest list, prune everything that doesn't apply to my partitioning, my partition filter. Then I'll go to the manifest file and I'll further prune if I have any other filters based on the column metrics. And anything that's left gets scanned. Okay. One more. Okay, and then we're going to do another query, but this one's going to be taking advantage of a feature called time travel. So instead of me just querying the current snapshot of the table, let me query the table as it was in the past. Why would I want to do this? Maybe I have a machine learning algorithm and I want to make sure I test that against consistent data. So I want to basically, I updated it 30 days ago. I would like to measure its performance against that same data set as it was 30 days ago. So that way I can compare the results. Or maybe I notice a sort of inconsistency in the data and I want to kind of figure out where the problem is. So I can go take a look at the previous snapshots of data that kind of look at the differences and kind of figure out what's missing, what's wrong, what's inconsistent, to do all that kind of QA work. So there's lots of reasons I may want to go be able to do this. But essentially what's going to happen is that in Spark, you would use this as of operator. Okay, how you do time travel does differ by engine. But you would use this as of operator and specify a timestamp. And basically what's going to happen is that it'll go to the catalog, get directed to the metadata file, but then when it gets to the metadata file, it's going to look at the timestamp on the snapshot. It's going to say, hey, is this timestamp on or before the timestamp in the query? Oh, it's not. So let me go to the next snapshot, which will be snapshot one, which is within our timestamp. So then it'll query based on that snapshot and then go through that pattern and look at that manifest list and then, do the query planning from there. So that's kind of how all that gets structured. Okay, before we do the Atlas case study, let me go back and revisit some questions. So let's see here. Here looks like table where you did that. Okay, files a format frequently used in data lake houses. Okay, I think that's an answer to the question. Can you have multiple different engines accessing the same set of data files? If so, does the API enforce? Oh, that's a great question because the answer is yes. You can have multiple engines, and basically what will happen is that let's say I am ingesting data with Flink. Okay, so I'm writing data. So technically, that job is going to be creating a whole new snapshot. But a read, so let's say I'm sending in a read from, let's say, like Dremio. That read is coming in. It doesn't care about that new snapshot that's being written because it's going to get directed to the latest committed snapshot based on the most recently committed metadata file. So so basically they don't interfere with each other. Now, what if I had two writers? Well, what'll happen is that at the onset of writing, they're projecting what their sequence is. So like they're like, okay, we have 5 snapshots, so I'm predicting that my write should be the 6th snapshot. So what's going to happen is that it'll write all the metadata, do the whole writing process, but before it commits the actual like metadata file, commits it to the catalog, it's going to take a look at the metadata file for the newest entry and make sure that it's still in the right sequence. So if I project that I'm number 6, then at the end of my write, now there's a number 6 there, and then I'm going to redo my rewrite based on the new commit. So basically, it uses what's called optimistic concurrency to basically facilitate multiple writers. And again, multiple readers or a reader and a writer doesn't matter because you have that snapshot isolation. The new snapshot being written will never affect the previous snapshots that people are reading. So that all works fun and good. Okay, our inserts do consistently or eventually consistency. If we do 8K queries per second and 4K reads per second, will there be inconsistent view? There shouldn't be. It is built to scale. Now what happens if you do have like a whole bunch of concurrent writers, what happens is that you can set a field, like you can set a setting that's saying, okay, you only have so many retries. So if it retries too many times, it'll just say, okay, we're not doing this right. But you can write as much as you want. Let's say you had one writer that is just writing that much stuff per second. That's fine. And if you have multiple writers, just depending on sort of like what the particular parameters of the job, that's fine. Now, if you're worried about consistency, that's where the thing I mentioned earlier, Project Nessie, and I'll talk more about that later on, comes in. So let's say so in the situation, let's say I like 5 tables that are typically used in a join. So the problem is, since they're typically used in a join, if I update the first table and someone comes in with a query and I haven't done the updates on the other 4 tables yet, they're going to get an inconsistent look at the data. But if I'm using Project Nessie with Iceberg, what happens is I can then create a branch, take my time, do all my updates on all 5 tables, and then merge that branch in. So that way all the changes for all 5 tables all show up at the same time. So that way my readers, they don't see, the shades of gray of the data. They're just going to see it from point A to point B. And that's the beauty of the whole sort of data as code paradigm that Nessie brings to the table. Okay. Cool. After some of this would be potentially result in a lot of old manifest files that I never read. Will Iceberg let me periodically prune old manifests? Yes, there are ways to maintain your table. What you do is you would expire snapshots. So there are like as part of the Iceberg libraries, there are procedures. So you can sit there and say, expire any snapshot before this date. And then it will expire those snapshots and clean up all the files. So it'll delete any data files that are no longer associated with the valid snapshot, any manifest files that are no longer associated with a valid snapshot, any manifest list. It'll just basically clean that all up. So there are ways to definitely maintain the table. Cool. And can that result in starvation? Let me come back to that at the end because I want you to elaborate on that. Okay. So for our next section, what I want to do is I want to show you like what this did for Netflix. Okay, because Netflix, they have their data lake, they were using Hive, and they were running into all those pain points that I mentioned earlier. But here we're going to focus more on performance. So basically, they have this system called Atlas, which had all this telemetry data that they would want to query. Okay, and basically 1 month's worth of data in this Atlas system equaled 2.7 million files across 2,688 partitions. So a lot of data. And the problem is, when they were using Hive, they could not process more than a couple of days of data at the time without the queries taking like days. Queries like this example query. So they needed to do something faster. So to kind of just give you an example, running a query on this Atlas data when they were using a Hive table with Parquet filters. So again, so basically it wasn't completely unoptimized. In this case, they did take advantage of Parquet filters, which just means like, hey, you're reading the Parquet filters and saying, okay, hey, I'm not going to scan this row group. I am going to scan this row group. Not going to scan this row group. So there is some optimization going on at the Parquet at the file level, but you're still opening up those files, closing those files, doing all those file operations. But at this level, you ended up having about 400,000 splits per day. Okay, so that means more splits, more individual things you need to scan. So this is not total 400,000. For each day's worth of data that was part of that query, that'd be 400,000 splits that had to be scanned. So in here, we're just running an explain query. So this technically the result of this query is just saying this is how long it took to plan the query. So in this case, it took 9.6 minutes to plan the query. They didn't even bother running the query because it would take too long. Okay, so 9.6 minutes just of planning. Now, when they switched it over to an Iceberg table, okay, so instead of tracking those tables with Hive, they're tracking it now with Iceberg. Same Parquet files, same exact data files. They're just now part of, you have Iceberg metadata using just partition data filtering. So none of that like, column-metric stuff yet. Just based on the partitioning by filtering by partitions, that reduced the number of splits to 15,218 total. Okay, so a lot less splits, a lot less stuff to scan. The result is the planning only took 10 seconds. The total execution time was 13 minutes. Okay, so it took basically almost as much time as it took to plan it with a Hive table took to execute the whole thing. Okay, that's a huge benefit, a huge performance jump. Now, of course, when we want better, so let's make it better. So now if we add in the min-max filtering, so that's when it actually looks at all the individual column metrics to determine, hey, does this file actually have any relevant data? relevant to my query. That narrowed it down even more to 412 splits. So a lot less data to scan. And again, a lot less data to scan is not just faster, but cheaper. Okay, less compute power that needs to be used, cheaper cloud bill. Okay, so that narrowed it down to total execution time of 42 seconds. The planning took 25 seconds, so a little bit longer, but the idea is it's doing that extra pruning, and that extra pruning saves you a lot of time scanning. So we were able to get that query that was going to take days down to 42 seconds. Okay, before it was 9.6 minutes to plan, it was 42 seconds to do planning and execution. Just to kind of get the idea, like, what is the benefit of this? So like now you're getting to a point where you can really use your data lake in the same way you use your data warehouse and have the same sort of features that you have in a data warehouse. Because now with ACID, basically with Iceberg, you get ACID transactions. So I can make smaller updates. I can do deletes. I can do updates. I can do merges. I can do all these types of DML transactions on my data lake in the same way I would do that work in a database or a data warehouse. And I can do it performantly at scale. Okay, that snapshot isolation, again, allows for a lot better concurrency. So you can have, again, a writer and a reader, multiple writers, multiple readers. You can facilitate all that concurrency, again, at scale. You get faster planning and execution because, again, you have all that nice tree of metadata that really allows you to plan a smart query for better performance. You're going to have better metrics because the metrics are updated on every write because technically all the metrics are coming from that tree of metadata. So in that case, the metrics are always pretty much ready to go. You're not having to do these long analyze scans. You're gonna have the ability to time travel. So I can go back and scan those previous points in time in the table, which you wouldn't be able to do with Hive, because basically what's in the folder is part of the table. Okay, so the older files couldn't stick around. You have table evolution. If I need to change, like I need to get rid of a column, add a column, rename a column, change a column's type, I can do that. And I don't have to rewrite the whole table. If I need to change, hey, I was partitioning by year, but now I want to also partition by month, I can do that. And I don't have to rewrite the whole table. Okay, and if I can save myself writing petabytes and petabytes of data, that's a win. Okay, so, and again, Iceberg, of the three main table formats, Iceberg is the only one that has partition evolution. So that's a unique feature to Iceberg. All engines can see the changes immediately because, again, you have the snapshot isolation. So literally any engine that you're using, they all have to go to the catalog, and the catalog is always going to be pointing to one metadata file. So all engines are, up until there's another commit, are going to be seeing that same metadata file regardless of where that's coming from. Okay, so again, you get basically this consistency not just within one box, but across all your tooling, across wherever your data is. And again, all ACID transactions. And you get all these, and they've added all these really cool features to further optimize. Okay, so you can now set up tables to be either copy on write or merge on read. Okay, which is great if you're doing like frequent updates. So basically what happens, usually you probably do copy on write, which just means, hey, if I updated like 5 records in this file, rewrite the whole file without those 5 records or with the updates. But with merge on read, what I can do is, instead of, if I'm doing a lot of updates, those writes are going to, build, all those writes are going to get, you're going to start seeing latency. So with merge on read, instead of rewriting the entire data file for the update, what it'll do is it'll just write a separate, what's called a delete file, to track those updates. And then it'll reconcile those on the read side. So that way you can boost up the speed of your writes. You can now take advantage of Parquet Bloom filters. So it'll actually write Bloom filters. Now you have Z-order clustering. So you have general clustering with compaction. So basically they have a procedure, so that way you can take a bunch of, let's say you have a bunch of small files, like if you're streaming and you're doing really frequent, ingestion, you're gonna end up with a bunch of small files. So you can run compaction, it'll take all those small files, turn them into condensed bigger files. But at the same time as doing that, you could also sort and cluster the data based on like a single column. But you can also do Z-order, where you can do it based on multiple columns and they'll be like equally weighted. So that way you just have that data clustered in a way that'll plan queries smarter. There's also metrics collection. So let's say you have like a 200 column table. Okay, keeping track of all the metrics for 200 columns is going to make your metadata really fat and hurt the performance of the table. You can do a fine grain tailoring of metrics collection. So you can say, hey, don't collect the metrics for these 150 columns, only collect it for these 50 or these 20 or these 5. So you can fine tune how the column works, so that way you only have the metadata you need, so that way you don't, for a wide table, you're not tracking so much metadata that it's slowing things down. Okay, Git-like semantic. Well, Project Nessie. Again, Project Nessie is a separate open source project, but what it does is it can be used as your Iceberg catalog and allows, basically versioning at the catalog level. So it does allow, again, first off, it allows those Git-like semantics. So I can actually create a branch of my catalog, isolate work, and then merge it back in. But the reason why it's important that it's at the catalog level, not at the table level, is because it now allows me to do multi-table transactions. I can basically commit things across multiple tables at the same time because it's across the whole catalog. I'm creating a split of the catalog, work on all the tables, and then I merge that back in, and all the updates across all those tables get merged at the same time. Because they are actually building an additional table level branching feature into Iceberg itself. But again, that'll be at the table level. So it shouldn't be able to facilitate like multi-table transactions. You'll still need something like Project Nessie to do that. The other nice thing about it being at the catalog level is that you're not tracking the changes to every individual file. You're only tracking the changes within the metadata. So that allows it to have a lot more throughput. So when you're doing a lot of frequent changes, you can track those commits at scale. That was actually, a lot of research they did when they were first doing this Project Nessie project, because they first thought, why not use Git? But Git just could not support the level of throughput needed for those like sort of high frequency writes. So Project Nessie was created. Okay. But yeah, so basically that's like Iceberg in a nutshell. I do have a lot of like articles and videos and stuff like that about all sorts of aspects of Iceberg. Do you want to learn more about Iceberg? There is the Iceberg website, iceberg.apache.org. They have a listing of blogs, which you can see at iceberg.apache.org/blogs. Again, I write for Subsurface. I'm part of the tech advocacy team at Dremio. Our specific team's like charter is really to go out there and educate people about open source technologies like Apache Arrow, Apache Iceberg, Project Nessie, Parquet. And we write a lot of articles about that, which you can find here at dremio.com/subsurface. Here's like the Iceberg section. Here's where there's like the official getting started tutorial for Iceberg. And actually a couple days ago, I came out with a new Apache Iceberg 101 course. So this actually has like a whole series of videos where I go over all the concepts, settings, all sorts of cool stuff with Apache Iceberg, and also just create a directory of all like the greatest tutorials all across the web. So like everything you'd ever want, Apache Iceberg sort of like in one page. So I would check that out. So that's all there. So check those out. And with that, time for more questions. So let me go bring up to see what we got for us questions. Okay, first I'll just start off with like, basically, Fitz, if you want to kind of like just elaborate on the whole like starvation question.
Sure. You mentioned the possibility that you were writing, several people are writing, and then you're writing, you think it's version 6, but someone's already got a 6, so you say 7. But when you do it, then someone's already got a 7, and so on and so forth.
Yeah, I mean that's a possibility. Again, it just depends on. I mean, those are things you'd have to tackle in the architecture of the system, because that's going to be the same for any table format, because they all use optimistic concurrency locking. Just because that's just the best way to do it for this particular context.
Right.
But yeah, so you'd have to probably take a look at how frequently am I writing, how long are those write jobs taking, and trying to figure out, okay, how many writers can we really support for our particular use case. But bottom line, you won't end up with inconsistent data in the sense that you won't have two writes, like a partial write being interrupted by another write or anything like that. A write, it either gets committed or it doesn't.
Okay.
Which is, yeah.
Cool, thank you.
No problem. And next, are hot manifest files cached in memory? At the end of the day, like Iceberg is, again, just a specification. So all those files are essentially being written to your storage, your HDFS, your cloud storage. Now, engines, based on like how they're designed, may do some level of caching. Like Dremio does do that. It uses it as a feature called the columnar cloud cache, which does cache a lot of the metadata on nodes. But that's going to be engine specific. So you'd have to want to look into like whatever engines you're using, what kind of caching mechanisms do they generally use? They're probably going to, it's probably will continue to apply to Iceberg tables as well. Wait, do we have a Slack channel? Yeah, like as far as the Slack channel, if you mean a Slack channel for Iceberg, there is an Iceberg Slack channel. If you mean a Slack channel for the meetup, I'm sure Pat will probably post a link in the chat soon enough.
Hey, Alex. Thank you so much for the presentation. It was really nice to know so much about the Iceberg. I do have a question, and it was a long, so I don't want to write it in the chat.
Go for it.
Okay. So let's consider we have like millions of records written per day, and then we are deleting million of records also on the same day. So we are doing this parallel processing at the same time, and we are also reading the records. I won't say in millions, but we are reading like 500 queries per second in a day. That is almost like 100K queries, more like that. Will this be a consistent view? Because every day we have things replacing the old things, and these are sometimes millions to billions of rows being written from
I mean,
SQL. I'm just saying from SQL perspective right now, but
it would have to be, because at the end of the day, like the catalog, because basically the idea is that all engines would communicate with one singular catalog. So in that case, whenever a delete happens or ingestion happens, a new commit gets made. So any engine communicating with that catalog is always going to be pointed to that newest commit. So it would be, the question we would just generally be like, with so many different jobs happening at the same time, question would be there with their making sure that if you have like, well, it would just basically would be come down to what your specific SLAs are, but like it would make it, you wouldn't end up with like a partial commit or inconsistent data. It would just be a matter of just making sure that you have everything set up to keep up with the pace. So that probably matter more with the particular engine you're using and the particular, like, let's say clusters like the particular like instances you use with that engine, to see if, like, if its performance can execute the queries quick enough to keep up with that. But again, you won't have like partial queries or anything like that, or anything inconsistent happening along the way if they're applying the Iceberg spec.
okay. And is there any limit on this Parquet format? I have heard actually first time this Parquet format. So whenever we store the data, does that convert it? Like if I have a key value store, does that convert it into the Parquet format and has a limit on the object size?
I mean, there are like ideal Parquet file size, like a Parquet file can be whatever size. Generally, I think if I remember right, the number I usually hear is like 512 megs. Is like generally like you ideally would. So if I had like, let's say a petabyte worth of data, I would want it broken up into a bunch of 512 meg Parquet files. And that could be done with there's basically using the compaction procedure in Iceberg. You can actually set up a job where it'll go back and rewrite all the data files to the specifications you want. So I can say, hey, rewrite my data, make sure that it's all 512 megs per, or 1 gig or 128 megs per file, and it'll rewrite the data in that regard. Now, as far as like how, and again, just to kind of reiterate what Parquet is just basically a binary data file format. And basically, because it's binary, it's going to be more performant over something like a CSV or a JSON file. Two, because it's a columnar file format, it's going to be more performant when running analytics in the same way, like, using data frames is more performant. But also what it does, it actually has like file level metadata. So basically what it does, it like has like these headers and footers, and it'll say, okay, hey, we have a group of rows, and then like here's a footer that gives you some basic summaries of like that group of rows that engines can then use, and like they can take a look at those descriptions of the row group and say, okay, hey, do I really want to scan this row? And basically optimize queries in ways that they couldn't with like a CSV or a JSON file.
Okay. Okay.
So it's
Thanks
just, yep.
for the answer.
Cool. Let's see here. You can see the Python side. The Python library looks like it lags behind the Java one. They are about to release a whole new Python library. Like they pretty much rebuilt it. So it should be released literally any day now. So it should have a lot more functionality when they do that. And it's also supposed to have a CLI, if I remember correctly. So that should be coming out soon. And for anyone who's like watching this on YouTube after the fact, probably already out by the time you're watching this. But yes, right now the Python library, it doesn't have the same functionality as the Java library, but that is sort of like on their priority list right now in releasing the new version of the Python library. Last thing I remember was that was similar to Iceberg was Data Lake. Could you speak to a comparison? So Delta Lake, okay, yeah. So Delta Lake, and bottom line is this: Delta Lake, Apache Hoodie, and Apache Iceberg occupy the same space. So basically, the trend right now is basically people are thinking, oh, my data warehouse bills are getting kind of expensive. At first this was all real nice, but now that we've ingested more data and we have more robust like workflows, these bills are starting to get really expensive. We're starting to see like
audio. I can't hear you, Alex.
Oh, okay. Did anybody else lose audio?
Can everybody else still hear you?
I can hear him.
Maybe it's just
You?
me.
Okay, cool. Okay, so people can hear me. Okay, cool. So bottom line, people are like concerned about their bills. So the idea and also performance. So basically you have this movement, the data lake house movement, which is the idea is like, how about instead of me doing all this work on a data warehouse and having to ingest my data first ingest my data to my data lake and then ingest my data to the data warehouse, how would I just stick to the data lake? That's going to be cheaper and easier and going to fix a lot of problems. But one of the key decisions you have to make when you're architecting a data lake house is to choose that table format. Because that table format, whether it's Delta Lake, Apache Hoodie, or Apache Iceberg, is going to be what determines what tools connect to your data and what features do they enable. Because each table format, they generally offer this most part the same set of features, but different engines are going to support them at different levels, which means different levels of performance, different feature sets at the engine level, and things like that. So that's sort of like the big thing right now. So generally, like Databricks really goes back like Delta Lake because they created Delta Lake. Over this year, you've seen a huge groundswell of support sort of outside of Databricks. So basically, you've seen like Dremio, Snowflake, Trino, Cloudera. Everyone kind of really had this groundswell of support going behind around Iceberg. So that you're starting to see like this sort of like Iceberg Delta Lake fight going on now. Apache Hoodie is there. They're doing their thing, and then they're I think like soon they're gonna come out with this company called One House that's gonna provide some services to support Hoodie. So they're still figuring out their spot there. So you have this like three-way sort of battle for who's gonna be sort of that gateway to the data lakehouse. But essentially, like they're trying to solve that same problem. Like, how do I find they're solving the same problem and they're trying to create the same features. They do it differently. Like Delta Lake, instead of having this like tree of metadata, uses what's called a delta log. So what it does, it just says from the last time I looked at the table to this time I looked at the table, what things are different. And it's just like one file, the next change. Hoodie tracks like this whole timeline and then like basically tracks, okay, here's a timestamp of a change, here's a timestamp of a change, here's a timestamp of a change. And again, generally they enable the same features, asset transactions through optimistic concurrency, time travel. Where they differ quite a bit is that Hoodie and Delta Lake both depend on the old Hive file storage. So that whole idea of like, hey, all the files in a folder are the table, they still pretty much work that way. And the problem with that is when you start using cloud object storage. So imagine, because that means your partitioning has to be done that way. And the problem is, what if I have a partition that has like 10,000 files? And now I'm getting a lot of requests for all those files when I scan that partition. And when I'm working with cloud storage, they often throttle requests. So too many requests like the same folder or the same prefix. So then what happens, you can run into potential bottlenecks when you have really large partitions, when you don't have that decoupling, which Iceberg does decouple. So in Iceberg, you can actually turn on a feature where it sets up the partitions differently. So instead of giving each partition its own folder, it'll actually create multiple folders and just kind of spread the files across multiple folders, so you don't run into that issue. It'll just use like hashes. And that's because Iceberg decouples. Instead of saying, I don't care what the folder is. All I care about is where those specific files are located. They can be in different folders, long as they're part of my list. As long as they're in my metadata list, we're good. And that's kind of one of the sort of the key distinctions and one of the key reasons why like a lot of people are getting behind Iceberg, because that really is scalable, especially when you're starting to see this big movement towards the cloud that's going on right now with the data lake and data lake houses. Any additional questions? Well, and thank you very much, Ellie. That was very kind. Thank you very much, Fitz. Cool. Awesome. But again, my name is Alex Merced. Please follow me on Twitter, again, at AM Data Lakehouse. And also add me on LinkedIn. I have several articles that are going to be dropping over the next few weeks on Apache Iceberg. I have one that just dropped a few days ago, the Apache Iceberg 101 course. And then, yeah, I'm constantly putting out content, and, just educating, entertaining, and enlightening.
Great, thanks, Alex. Hopefully everybody can hear me now. So.
Yep.